I recall that in crystalline solids, the particles are arranged in a regular three-dimensional pattern known as a lattice.
Correct. And every lattice is made up of lots of subunits called unit cells.
That means the unit cells repeat one after another to form the lattice, and finally the crystal?
Well said. So to understand what gives crystalline solids their shapes and their other physical properties, you must understand the geometry of the unit cell and how the atoms are joined together in it.
I understand. That's the bonding between atoms that join them together.
Exactly.
Got it. So, teacher, in earlier lessons, we've learned that sodium chloride and magnesium oxide exist as a giant ionic lattice. What sort of other lattices are we going to discuss today?
Well, the AS and A-level exams will test your knowledge for the giant ionic lattice, simple molecular lattice, giant molecular lattice, and giant metallic lattice.
Ooh, that's a lot of structures we need to know. Let's begin.
Sure. Let's start with ionic crystals. First things first, do you remember how ionic bonds are formed?
Yes, I do. For the formation of ionic bonds, two different ions of different charges, that is, positive ions and negative ions, are required.
Correct. When the cations and anions are bound together by ionic bonds in a regular repeated pattern, a giant ionic lattice is formed, as seen in sodium chloride and magnesium oxide.
Yep. In sodium chloride, each sodium ion is surrounded by 6 oppositely charged chloride ions, and each chloride ion is surrounded by 6 sodium ions.
Correct. To add to that, the number of chloride ions that surround each sodium ion is called the coordination number of the sodium ions.
Hang on. What is this coordination number?
Simply put, the coordination number as the number of atoms, ions, or molecules that a central atom or ion holds as its nearest neighbors in a crystal.
I see. So that means in sodium chloride, the chloride ion has a coordination number 6, and this is the same for the sodium ion.
Correct. Additionally, the chloride ions are much larger than the sodium ions. The sodium ions fit into the spaces between the chloride ions so that they are as close as possible to them.
Got it.
And Divash, what about the structure of magnesium oxide?
If I recall, magnesium oxide has the same lattice structure as sodium chloride. So, we can simply replace the sodium ions with magnesium ions and chloride ions with oxide ions.
Exactly. So what kind of properties do these giant ionic crystals have?
Due to strong electrostatic attraction between cations and anions, they are hard solids and have higher melting points.
Good. They also do not conduct electricity when solid but become conductors when molten or in solution form.
I know the reason for that. When they are solid, there are no delocalized electrons or free ions to conduct electricity. However, when they are molten or in an aqueous solution, the ions break free to become free mobile ions, which can then conduct electricity.
Good job. And as you've learned from earlier chapters, most ionic crystals are soluble in polar solvents like water.
Yes. I've also learned that polar solvents like water decrease the electrostatic forces of attraction, resulting in free ions in an aqueous solution. Hence, ionic compounds dissolve in polar solvents.
That's right. Now let's move on to our next type of lattice, the simple molecular lattices.
What are these? Are they made up of simple molecular substances?
Yes, these structures are made up of simple molecules which have strong covalent bonds between the atoms, but have much weaker forces holding the molecules together.
So, in this case, I guess there is no chemical bonding between molecules.
Yep, these weak forces are dipole-dipole forces, instantaneous dipole forces, or hydrogen bonding attractions which are comparatively weak. For example, the molecular lattice of iodine consists of a neat arrangement of molecules in a crystal lattice, which is held together by the weak intermolecular forces.
I understand now. These weak attractions mean they are easy to break and hence their melting and boiling point is low.
Exactly. Being a nonpolar molecule, the weak intermolecular bonding in iodine is due to instantaneous dipole or induced dipole interactions.
Although the molecules or atoms are packed tightly, only a small amount of thermal energy is required to overcome intermolecular forces and break the lattice.
Nicely explained. Do you know any of the other properties of a simple molecular lattice?
Since they have covalent bonds without delocalized electrons, they are non-conductors of electricity.
Correct. In addition to that, simple molecular lattices also can't conduct electricity even when molten because they don't have the ions.
Got it, teacher. How about their solubility?
The same rule sticks. Since iodine is nonpolar, it is insoluble in polar solvents like water.
Want to learn more? We have additional learning resources to offer for Cambridge IGCSE and AS A-level subjects. Register now for free.